Hello friends. In this video, we will look at creating our own Zigbee sensor based on a module from Seeed Studio, ESPHDTBZ, for which we will make the firmware in the ESPHome builder. To make it more interesting, we will build something that, at least at the time this video was released, did not yet exist as a factory-made product, a 3-channel dry contact sensor which, combined with an optocoupler with the same number of channels, can be used as a sensor for detecting the presence of electricity on 3-phase power lines. As detailed as possible, with specifics, life hacks, and a ready-made example of working firmware code. More on all of this, and for now, by tradition, I ask you to like this video so that more people interested in the smart home topic can find it, and to subscribe to my channel if you have not done so before. For my experiments, I took this kit from Seeed Studio. It comes in a small green box. On the front side, there is a schematic image of the board and an X3 mark, meaning there should be 3 pieces inside. On the back side of the box, there is a little more information. Here, the specific model of the kit is already indicated. Seeed Studio Xiao ESP32C6. There is also a serial number and manufacturer information. The only unclear point is the date December 23rd, 26. Apparently, this is not the production date, because it is in the future. Possibly, this is the validity period of some marking or an internal batch designation, but this cannot be deciphered from the packaging itself. Inside the box, everything is placed in a plastic tray. The kit really does include 3 Xiao ESP32C6 modules with USB-C connectors. The contacts on the boards themselves are not soldered, so the modules can be used as is, or, if necessary, the included pin headers can be soldered on. They are also included in the kit. The module is very compact. The board measures 2 by 1.8 centimeters. A USB-C port is soldered onto it on the sides, of which 2 small buttons can be seen, boot and reset. Along the long sides of the board there are contact pads for soldering. Their pinout is printed on the back side of the board, VBUS, GND, 3v3, and digital pins. In the center, service pads are visible, including boot, and below them, back contacts for connecting a lithium battery, which can be charged from the USB-C port. Now let us move on to the software part. To begin with, on the Home Assistant test server, I installed ESPHome Device Builder. It is installed in the usual way through the Home Assistant Applications section. In the list, it is enough to find ESPHome, install it, and launch it. After that, we get an environment in which firmware can be created. We launch the add-on and click the button to add a new device. The setup wizard starts. Here we click Continue. In the next window, we choose the option to create a new device. Now we enter the device name, as well as the name and password of the Wi-Fi network it will connect to. This is a normal standard step, even when creating a Zigbee device. Further on, we will adjust everything at the firmware level. Here we select ESP32C6. Although right now this also does not matter, everything will be edited later in the firmware code. And the final step, where the key required for connection is displayed. It can be obtained again at any time later. At the bottom, click Skip. A tile for the new project appears. We go into the code editor. This is what the basic code generated by default looks like. The device name and type, network connection data, the key for connecting to the device, emergency mode. And this is my firmware version. In the ESP32 section, the version has been corrected and the memory size has been added for megabytes. Logging is enabled. The Wi-Fi section, I left it for now, but I will say right away, it can be removed. Next, a Zigbee section has been added. Here the ID, model, device type, and device, not router, and power type are specified. Then come the binary sensors. There are 3 of them, according to the number of phases I want to monitor. They are tied to GPIO1, GPIO2, and GPIO21, respectively 3 consecutive physical inputs, D1, D2, D3. The device underscore class, power is specified. Pull up is enabled for each input. This is needed so that the contact does not remain in an undefined state and does not catch random interference. In the idle state, the input is pulled up to a logical 1, and then due to ESPHome inversion, it shows the sensor as on only when voltage is present. At the end, small delays are added for each input, 200 milliseconds for switching on and 500 milliseconds for switching off. This is needed to filter out random short pulses and avoid false switching. Now it needs to be checked. Save the firmware and exit the editor. We validate it to check how correct it is. And in the first version, validation failed for me. And all because when there is a Zigbee block in the firmware, it is not possible to enable the emergency Wi-Fi access point. I deliberately left this moment in the video so that when creating your own sensors, you do not step on this rake. This block must be removed. For now, I am leaving operation through Wi-Fi. Here is the working firmware version, taking into account parallel support for two interfaces, Zigbee and Wi-Fi. Save it. Now validation passes successfully. The firmware can be compiled. Press install. I will flash it via USB, so in the next menu I choose manual mode. The flashing process, especially the very first one, is quite long and directly depends on the availability of free resources on your server. First, the system determines the list of necessary libraries and downloads them. Then the firmware itself is built. Nothing needs to be done here, we just wait. After the firmware has been built, a new dialog will open with a choice of flashing options, with reset to factory settings or just a current update. In our case, we choose reset to factory settings. Now the firmware is fully built and a download button has appeared at the bottom. Click it and download the .bin file. This is exactly the file that we will write to the ESPHDTBZ. For writing the firmware, it is most convenient to use ESPHome web. I will leave the link in the description. Before flashing, connect the board to the computer via USB-C and the indicators on the module will light up. After clicking connect, the browser shows a list of available serial ports. Here you need to select exactly the port on which our ESP32C6 was detected. In my case, this device appears as USB JTAG/serial debug unit. Select it and click the connect button. Now click the install button. By the way, instructions often say that you need to hold down the boot button on the board before connecting. I did not do that even once. I simply connected it and could flash it right away. In the next menu, select the compiled firmware file that we just created and start the writing process. The writing process is fast and, if everything is done correctly, ends with a message about successful configuration installation. Since in this firmware we have not only Zigbee but also Wi-Fi. In the ESPHome builder, the device tile should show the status as online. You can go in and look at the logs. To test the operation, I alternately shorted the GND contact with contacts D1, D2, and D3. In the logs, this is displayed as switching the phase sensors on and off. When the contacts are closed, it means voltage is present on the phase. When open, it is not. Now it is time to share some life hacks that can save you time and nerves. The first problem I encountered was the module's unwillingness to connect over Zigbee. In the logs now, you can see that connection attempts are being made, but they are unsuccessful. I was stuck here for some time, tried different options, for example removing Wi-Fi and switching to Zigbee only, but nothing helped. Still, I managed to identify the problem. This is my test server and the Zigbee 2 MQTT installed on it. The system itself is current, but the coordinator is old, still with firmware from December 26, 2022. True, there are usually no problems with it, but in this case the ESP did not want to connect. But with one of my 3 working Zigbee 2 MQTT setups, where the coordinator has firmware dated March 10, 2026, there were no connection problems anymore. Here in the logs you can see a successful connection. In both cases, the Zigbee 2 MQTT version is 2.12.0. The coordinators are based on CC2652. The channel is 15 in both places. The only difference is the firmware of the Zigbee module. There is, of course, no official converter for ESP, since this is a builder, but Zigbee 2 MQTT can now generate them automatically, so do not let the not supported label bother you. In this version, it is an end device, and below the names specified in the firmware have been pulled in. On the Exposures tab, 3 binary sensors, they are open now, so the state is off, and the signal quality level is shown. Test. I short GND and D1, and the first sensor is triggered. Everything works as intended. Power consumption when working with such firmware. Let me remind you once again that both Wi-Fi and Zigbee are active right now, is 0.327 watts. For a battery-powered device, this is too much, so it should be considered for stationary power. An external battery can only serve as a backup power source, not work continuously. I happen to have this lithium battery rated at 3.7 V with a stated capacity of 1000 mAh. If converted into energy, it gives about 3.7 Wh. Taking into account the module's power consumption, under ideal conditions, such a battery should last about 11 hours of operation. In practice, the result will be less. I would estimate about 8 to 10 hours of continuous operation. That is, as a backup power source, so that the sensor can send data when external power disappears, which is exactly its task. As I already mentioned, the module from Seed Studio already has contacts for connecting a battery. There is no need to invent anything here, just solder it observing polarity. Moreover, battery charging logic is provided here. It happens automatically when external power is connected. The charging process is indicated by a blinking red LED, and after the battery is charged, it will go out. Here is the power consumption during charging, 0.933 watts, that is, about 0.6 watts goes to the battery. Speaking about my model, a full charge from 0 to 100% will take about 7 hours. Checking the operation is quite simple. I disconnect external power and short GND and D3. The third sensor is triggered. Everything is correct. 3 years ago, I made a video tutorial on creating an electricity sensor based on an optocoupler and a Zigbee door sensor. The link is in the description. The logic here will be similar. Only the optocoupler has 3 channels. On one side, a common neutral and 3 phases are connected. On the other, 3 outputs. From each phase, GND, and power for the optocoupler. Unlike the single-phase version, which works without external power, here it is needed. The backside of the board. The high voltage and low voltage parts of the board are galvanically isolated. Optical coupling is used here. For convenience, I soldered the included pin header onto the module and, in this inverted form, to see the pin numbering, soldered it onto a small prototyping board, which matched the length of the optocoupler. The battery is hidden under it, and on the right you can see the connection point. The red wire is plus, the black one is minus. On the left side, 3 red wires. These are the 3 phases from the power grid. The black wire is the common neutral. They are connected to the terminal block of the high voltage part. Voltage is present, so all 3 signal LEDs are lit. On the right side, the ESP connection. Outputs D1, D2, D3 are connected to the corresponding outputs of the optocoupler, then the yellow wire, module GND to optocoupler GND, and the red wire, power, goes to the battery plus from the VCC contact of the optocoupler. Although in this video I focus on the Zigbee interface, Wi-Fi, the classic option for ESPHome, has also not been cancelled. Moreover, in this firmware version, you can work simultaneously over both Wi-Fi and Zigbee, for example, to improve fault tolerance. For connection and Home Assistant, the standard ESPHome integration is used, which automatically detects the new sensor. A key is required for connection, the same one specified in the firmware code, in the API section. The integration passes the same 3-phase sensors into the system that we already saw in Zigbee 2 MQTT. In this case, the same sensor is added to the system twice, through ESPHome and Zigbee 2 MQTT, and they react to the disappearance/appearance of voltage on the channels synchronously. Here at one moment in time, voltage is absent on the first phase and present on the second and third. For now, this is what the finished assembled sensor looks like. I was lucky that I found a prototyping board matching the size of the optocoupler, and I managed to connect them. Right now, all 3 phases are active. All the LEDs are lit. And now, there is no voltage. The LEDs have gone out. In principle, all that remains is to add a low-power miniature 5-volt power supply as the main one for the ESP32, and it would be nice to add a small external antenna and place it, for example, in a standard electrical installation box. Let us check it in real time. On the left, these are the data coming over Wi-Fi through ESPHome. On the right, over Zigbee through Zigbee 2 MQT. Voltage is present on all phases. We record a power outage, almost completely synchronously. Similarly, power appearance, so it can be used through any interface and even both at the same time. Another example, disconnecting one of the phases, the first one. Both integration options work correctly and simultaneously. And finally, the final assembly. I decided to leave only Zigbee, so I simply removed the block related to Wi-Fi, and along with it API and ODA. And in the Zigbee block, I set the operating mode as a router. I did not touch the binary sensors. They are quite simple. There is nothing special to add or remove here. Save, validate, and compile the firmware. In Home Assistant, remove the sensor from both ESPHome and Zigbee 2 MQTT. I flash it via USB and open the log window in the ESPHome Flasher web interface, since access over Wi-Fi through the builder is no longer available. By the way, one more life hack. If the device behaves strangely, does not want to flash or connect, here, in this same log window, there is a Reset Device button that fixes most problems and is more convenient than the tiny button on the board. Reconnect to Zigbee 2 MQTT. And one more life hack. If you experiment with firmware, repeatedly connect and disconnect the device, then Zigbee 2 MQTT may get stuck. In my case, it stubbornly showed that this was an end device, despite the router firmware. The fix is to restart the add-on itself in the Applications menu. After that, everything connects correctly. Now it is a router. Everything else works the same as before. So far, I have not added anything new to the firmware, but I may experiment with a voltage divider and displaying the battery charge level. Power consumption without Wi-Fi is slightly lower, but insignificantly so, 0.3 watts. For a battery-powered sensor, this is very high. So for now, only stationary power should be considered, and the battery as a backup power source. Designing your own Zigbee devices has now become so simple that absolutely anyone can do it. This truly opens up new possibilities. You can solve tasks for which there are no factory solutions yet, and literally in 10 to 15 minutes without much effort. Write in the comments which sensors you personally are missing and which would be interesting to create yourself. Perhaps we will consider some of these cases in the next lessons. That is all. I hope the video was useful and interesting for you. I will be grateful for your likes. They help promotion on YouTube. If you do not want to miss new reviews and lessons, subscribe to my channel. In the description under the video, you will find all the necessary links to devices, text materials, videos on this topic, as well as my social networks, Telegram channels, and a group for communication on smart home matters. Thank you for your attention. See you again. Peace to everyone.